Today, the topic that we will cover is the topic of dynamics, which is kinematics of particles, and this is the coverage of chapter 11. The chapter is taken from the textbook Beer and Johnson. In this section, in this chapter, we're going to cover the following. Okay, I'm going to cover the following, which is rectilinear motion, position, velocity and acceleration, and then determination of motion of the particles, and then uniform rectilinear motion, and then several particle of relative motion. Okay. These are basically, I think, most of you are already familiar. Because from my list, you are not the first timer that was taking the subject. Some of you have taken 4 times, 3 times, 2 times, and first time. Very few are first time. So we start by, okay, this slide I have explained yesterday. Okay, I've explained yesterday the concept of kinematics and kinetics. Okay, and then yesterday I have mentioned also what different type of motion. Okay, and this one is first type is rectilinear motion. Okay, rectilinear motion, and then with that type of motion we talk about position, velocity, acceleration. Okay, as it moves along a straight line. Okay, that is a rectilinear motion. And then another one is a curvilinear motion. Okay, so keyword for curvilinear motion is a curved line. Okay, so a particle move along a curved line. Okay, in 2D or in 3D. Okay. This one I have explained yesterday, different type of motion of the particle. Okay, it can be we are using a rectangular coordinate x, y, z. Okay, and then it can be looking from a polar coordinate point of view, and then it can be also in the spherical coordinate system. Okay, and then last but not least is normal and tangential. Okay, all right, and this coordinate we can measure from fixed reference axis or from moving reference axis. Okay, okay, this one is the elaboration of the concept of rectilinear motion. So we want to find position, velocity, and acceleration. Okay, if you see here, we have a particle. Okay, move along a straight line. Okay, move from 0 to P. Okay, so the distance is x. Okay, so every one section here, one cut here is 1 meter. Okay, so from here to the right, and then from here to the left, To the right is P, particle, and then to the left is P prime. Okay. So to the right is a positive, and then anything to your left is negative. Okay. So that's why we define here O. O is a datum basically. Okay. This datum. Oh, by the way, before I forget, did you see my slide? Because I'm the one, I'm talking for 1 hour, and then at the end, in the end, student cannot see my slide. Please respond. Okay, yes. Okay, thank you. I could just show to make sure. Okay, to the right is positive. Okay, okay, and to the left is negative. Okay, so that's why this zero we call this datum. Okay, so remember, datum is point of reference. Okay, point of reference. We set our datum, but normally from our, through our norms, not the new norm, norms, to the right is positive, to your left is negative. Okay, we set the datum. Okay, this one is, we take an example of motion of particle. Okay, motion of particles. This motion of particle, the basic equation is as a form of function. Okay, form of function here, this one, x equal to 63 square minus 3 cube. This is the graph of x versus time. Okay, graph displacement versus time. Okay, so we can plot this graph, okay, to be as the following. Okay, so we have x equal to 60 square minus t cube. Okay, all right. Okay, this slide, what this slide shows is basically how we do the derivation. Okay, consider particle, and then we move from one location to another. Okay, P to P prime. We have here x, and this is delta x. Okay, this is x, this is delta x. So basically, when we say position particle, position P at time t and P prime with t plus delta t. So we have the instantaneous velocity. Okay, so we can get the value of v equal to dx dt. Okay, dx dt. This is basically show you how to get the value. Okay, and instantaneous velocity also can be positive or can be negative. Okay, if positive here, see, velocity is positive, and here going to the left, the velocity is negative. So the equation that we have taken earlier, okay, when this is a previous equation, previous equation. This one, yeah, x equal to 6, x equal to 60 squared. So what we will get if we differentiate this one with respect to time. Okay, so we have here x. Okay, x equal to 60 squared minus t cube. So you differentiate with respect to time. What do you get? Okay, so you get 12t minus 50 squared. Okay, so you differentiate that with respect to time, and then you plot the graph. Okay, you plot the graph. Okay, and then next one, we differentiate another time, so we can get acceleration. Okay, with the positive acceleration, instantaneous acceleration. Okay, positive velocity, we get positive velocity, or decreasing negative velocity, and then negative or positive. Okay, this is an instantaneous acceleration. If the equation just now we differentiate again with respect to time, okay, so you can plot the graph as the following. What does it mean with this graph is as time goes, the particle is slowing down, okay, from 12 going down to minus 24, okay. The next slide, I will show you different type of motion condition, okay. When we want to find the motion of the particles, okay, we want to uh, determine the velocity, okay, the velocity and position, okay. So there are three classes of motion, okay. One of it is A as a function of time, okay. This one, A as a function of time, okay. Number two is A as a function of position. And number three is A as a function of velocity. So we're going to look at these three types of motion, okay. A as a function of time, okay. The first one, acceleration as a function of time, and then number two, acceleration as a function of position, and then the third one is acceleration as a function of the velocity. Okay, it depends on what type of question that we are dealing. Okay, and we also have a special case. Special case means the value of A is constant. Okay, what is meant by A is constant is we mean by saying that it is uniform accelerated rectilinear motion. Okay, and acceleration will be zero. Okay, when the velocity is constant. This is uniform motion. Now, the next slide will show you how do we obtain, okay, the value for acceleration as a function of time. Okay, for this one, if you look at for this one, for case number one, we have here case number one. Okay, this is case number one. Acceleration as a function of time. We start by writing what is acceleration. Okay, acceleration basically for this one. Okay, acceleration. Okay, we start to write. Depend on the nature of the question. For this case, acceleration is function of time. So we start writing the dvdt. Okay, dvdt is acceleration. Okay, so it is as a function of time. Okay, right? So you cross multiply both sides. So you get dv equal to ft and then dt, right? After that, we would like to integrate both sides. Okay, so you have to integrate both sides. Okay, integrate both sides. Okay, so this is dv. So you start with initial velocity, and then vt. Okay, and then the time ft dt 0 to t, and then you integrate this one, you get Vt minus V, okay, V dot, okay, equal to, okay, Ft dt, okay, right? So this is the value that we get, okay, for the first one. This is the velocity, okay. How about another one, which is the displacement. For displacement, we start from here. Remember, always remember. I would suggest all of you need to have one sheet of formula. We call it formula sheet. So important formula we already have at hand, rather than have to look at different places. I put it one, because when during the quiz or during our open book test or open book exam, you need to organize your material, your notes, your book, so it is in order. So it is easier for you to look or to refer. Right? So my advice is you must have one formula sheet with you. Okay, put it one piece on a piece of paper, and then it's easier for you to refer. Okay, so we start by writing here dx dt. What is dx dt? Dx dt is the velocity. Okay. Oh my my pen jumping here and there. Okay. Okay. So dx dt basically is the velocity, right? The velocity. So we cross multiply both sides, you get dx. Okay. So we have dt. Oh, nice. Jumping here and there. Okay. So we have here. Okay. So I have vt. Okay. And then dt. Again, what we do the same thing. We integrate both sides. Okay. We do the integration for both sides. Okay. This is dx, so we start from initial x to xt. Okay. And then for the velocity, since this is time, start from 0 to time. So we solve, so it's going to be xt minus x dot, okay, x dot x dot, okay, equal to the integration of vt. In dynamic, the starting point is very important. Okay, make sure you choose the right equation, right formula, um, have the right free body diagram. If not, the rest will be useless. No point will be given for wrong equation and wrong step. Okay, next one. Okay, I have done this one. This is a as a function of time. Okay, let me clear erase all on the slide. All right, we have done doing the first part, which is acceleration as a function of time. This one, acceleration as a function of position. Okay, when we have acceleration as a function of position, we start by writing a as a function of fx. Okay, a as a function of fx, and we start by writing here v equal to dx dt. Okay, v equal to dx dt, or we take dt, put it in front here, so we get dt equal to dx divided by v. Okay, dx divided by v. All right, starting from here, dt equal to dx divided by v. Okay, since we have here a equal to dv dt, okay, we know that acceleration equal to dv dt. So we can substitute, okay, substitute this dt into here. So we are going to get acceleration equal to velocity times dv dx, okay, equal to acceleration as a function of fx, okay. Okay, this is what we call the starting point of it, okay, the starting point of it. And then after we have obtained the acceleration in this form, okay, in this form, we can use the same technique as above, okay. So we can get, we cross multiply for both here, so you can get v dv, and then you get fx dx, and then you integrate both sides, okay, you integrate both sides, so you're going to get half vx squared minus half v dot, okay, square equal to the integration of fx dx, okay. This is for the second case, acceleration as a function of position, right? And then we move to the third type of motion of a particle, okay, is acceleration as a function of the velocity, okay. All right, acceleration as a function of velocity. So we start by writing dv dt equal to acceleration equal to fv, okay, and then we take this one dv divided by fv, and then equal to dt, okay, equal to dt. This is the way we arrange, okay, arrange the location of this equation, okay. So we bring dt here, okay, we multiply both sides by d, okay, by dt, so you're going to get dv divided by fv equal to dt, okay. So you integrate both sides, okay, integrate both sides, okay. So when we integrate both sides, you can to get as the following, okay, dv divided by fv, and then you do the integration, okay, and then we follow the same step, okay, like earlier slide. The final one, you're going to get xt minus x dot, the integration of v dv divided by fv, okay. Normally when we are dealing with this type of acceleration function, okay, acceleration as function of velocity, if we are dealing with this type of equation, we need to remember the formula, how to do the integration for natural log, for example, right? For natural log, what will be the integration? So that one you have to recall what you have learned before in your high school or during your matriculation before, okay, in mathematics, additional math, right? This is an example, okay. I think this one you can go through on your own. Um, simple, okay. Okay, we look at this example. Okay, we take example 11.3. Okay, I give you 1 minute to read this example. Through my experience, we give student the quizzes or okay, related to this topic. Almost everybody they cannot answer this type of question, right? So in this case, we see acceleration as a function of velocity, right? Okay. So I give you 1 minute to read this question. Okay, we continue. You can see here, this is a brake mechanism, okay, used to reduce gun recoil, consists of a piston. Okay, engineer, we talk about piston, piston attached to a barrel moving in a fixed cylinder filled with oil. Okay, and then as barrel recoils with initial velocity v dot. Okay, uh, this barrel has initial velocity v dot. Okay, piston move and oil is forced through orifice in piston, causing piston and cylinder to decelerate at a rate proportional to their velocity. So in this problem, we have to find the velocity, to find xt and vx. Remember, vt, vxt, and then vx. Okay, velocity as a function of x. Okay, this is a basic question given. So the first thing you need to do, the strategy, our strategy is we have to integrate acceleration. Okay, acceleration. We know that acceleration equal to dv dt. Okay, equal to minus kv. This one is given in the problem. Okay, this is the first thing you need to do, and then we need to find the velocity of t. Okay, find the velocity of t. Do the integration of this equation. Okay, so this is the key. Okay, this is the key. The key for this problem. Okay, acceleration as a function of the velocity. Okay, we know that a equal to dv dt equal to minus kv, and then we find vt. This is the first one. Okay, first one. Next one, we have to integrate VT. Okay, in order for us to find the velocity of xt. Okay, so we know that Vt equal to dx dt. Okay, very simple. Vt equal to dx dt. Okay, and then from here we can find xt. Okay, find xt. And find xt. Integrate Vt, and then we find xt. Next one. The third one. Remember the equation that we have do the integration in earlier slide. We want to integrate because here we want to find Vx, right? So we need to use the integration of V dv dx. A equal to V dv dx minus kv. Okay, equal to minus kv. And then from there we can find Vx. Okay. So in dynamic, it's like that. Cannot simply, it's not mathematics only, not mathematics per se. Mathematics is a tool, but how do you apply the concept is much more important. What or which equation that we need to use, okay, is very important. That's why you need to read the question carefully. You need to read the question very carefully, read line by line, try to understand, okay, what is required and what is known. Because through my experience, students, they didn't read the question carefully. Sometimes we change the number or we change the direction. Okay, a different student, we give even the similar question, but we put different direction or different sign, different value, and then at the end of the day, student they answer it wrongly. Okay, answer it wrongly. All right. So these are the steps, the steps for you to solve this problem. Okay. So basically, this is the three important concept or equation that you can use. Okay, to solve this problem. Okay. These are the detail, the mathematics of it. You do the integration, you find BT, and then you get the final answer is going to be like this. Okay, you do the integration of this one, you get the answer in exponent, and this is mathematics, right? So you get velocity equal to V dot equal to E to the power of minus KT. Okay, if you want to get the detailed answer of it, you get the textbook, Beers and Johnson. Okay. In that textbook, it will give you the detailed solution of this example. Okay. The second one is we do the integration. Okay, we want to find xt, and then we get this value. Okay, so the graph is going to be like this, going up, and then this is the limit, the maximum value of it, which is v dot divided by k. Okay, this is the first one, the second one. Okay, and last but not least is the integration of acceleration to find Vx. Okay, so you get Vx. Okay, this the graph is like this. Okay, you get V equal to V dot minus Kx. Okay. All right, I finished that part. That example. I hope you can go through on your own. Okay, the example 11.3. Okay, on your own in detail. Because through this medium, we don't have much time or luxury time to go into detail of that one. Okay, I only highlight the fundamental aspect of it, and then the rest is up to you to do and to revise. The next concept is uniform rectilinear motion. Okay, okay. As I mentioned in earlier slide, For the particle in uniform rectilinear motion, acceleration is 0. Okay, and the velocity is constant, right? When the velocity is constant, okay, when you differentiate the constant, you differentiate 5, 8, 10. When you differentiate the constant, it will become 0, right? So we have here, start from here, dx dt equal to v equal to constant. So we do the integration here, okay? The integration for this one, you get dx, you integrate both sides, okay? You put here, uh, we get dx dt, okay? Equal to v. So multiply both sides, you get dx, uh, you get v dt, right? And then what you need to do, you integrate both sides, okay, limit from x dot to x, and then from 0 to t, okay. So you get x equal to x dot plus bt. I think you're familiar with this equation, okay, because we have went through all of this quite some time. V equal to x equal to x dot plus bt, okay, x equal to x dot plus bt, okay. And then the next one is v equal to v dot plus at. Okay, this one also you're familiar. Uh, so this line just show you how to obtain this value. Okay, right? So you get, when the case of a constant, we get v plus v dot plus at. Okay, same thing for the next one. Okay, for the case of acceleration of particle constant, you get here x equal to x dot plus b dot t plus half at squared. So the keyword here, when the acceleration, okay, of the particle is constant. Okay, all right. Therefore, we can use this equation. Okay, and same thing for this one. We get b squared equal to v dot square plus 2as. Right? Okay. So all of this is 2, this is 3, this is 4. Okay. All of equation we can use in the case of uniformly accelerated rectilinear motion. Okay. Okay. Finish that one. Uniform accelerated rectilinear motion. Another one is what we call a relative motion. Okay. This concept is also very important. Okay, so I want to explain this slide slowly. Okay, motion of several particles, relative motion. Okay, so look at this figure. Okay, we have the particle. Okay, move from origin. Okay, the particle, they are move along the same line. This is the line. They move along the same line. Okay, they start. Okay, start here. Okay, and then the displacement. How to measure the displacement? We measure the displacement from the same origin and from the same direction. Okay, so we have here the particle A. Okay, and then we have here is particle B. Okay, so we have here particle A, and then this is particle B. Okay, particle A, particle B. Start from here. We measure here. Okay, measure here, we have here xa. okay, and then we measure, so from the same origin, from here to here, right? This is XB, right? XB. Both must be measured from the same origin and the same direction. Okay, same origin, same direction. Okay, okay. Now we want to find what we call the relative velocity. If I want to write the velocity, for example, here I say XB, XB relative to A. Okay, XB. What is XB relative to A? It is a relative position of B with respect to A. Okay, so I write XB slash A like this. So the way we say it is like this. XB relative to A. A relative position of B with respect to A. Okay. A relative position of B with respect to A. Okay. All right. So what is that? It's basically if XB relative to A means B minus A. Right? B, this B minus A. So we have here XB, okay, the distance from here to here, XB minus XA, okay, right? Therefore, if we bring XA, okay, to your right hand side, it's going to be XA plus XB relative to A, right? This is the fundamental of how do we write the relative motion, okay, for several particles. Once you have set up this correctly, when you want to find the velocity or the acceleration, it will follow the same order, okay, same order, right? So here we have the velocity, okay, velocity B relative to A equal to BB minus BA, and then acceleration B equal to A, acceleration A plus acceleration B relative to A. Okay, remember this one. All right, another one, another concept. So is a pulley concept. Very popular concept and important for us to understand. Okay, for you to understand. We are dealing with pulley system. Okay, okay. For pulley system, the important concept that you need to know. Okay, this one what we call the concept of dependent motion. Okay, concept of dependent motion. So we have here, okay, we have here the pulley system here. We have a position of block A. Okay, this is block A. The position of it is XB. Okay, measured from here. Okay, from this link going down, this is XB. And what else I would like to highlight? Okay, this is position A. Okay, block A. This is block A. This is block B. Okay, and then we have here XB and XA. Okay, to connect between these two blocks, okay, which is block A and block B, okay, it is connected with a constant rope, okay, constant rope, okay. This is a rope, okay, rope, and then it is wrapped around this pulley, and then going down, been wrapped again, E and F, and then going up, okay, and it is hook at point G. Okay, all right. The main thing that we need to know that the rope, okay, the whole rope, whatever happened, this rope, it has a constant length. Okay, so rope constant length. Okay, and the sum of the length of the segment, all of this, the sum of this rope must be constant. Okay, therefore the way we write is going to be as the following. So we have here XA, okay, XA plus, okay, 2XB, okay, equal to the total rope, total length of it, which is constant. Okay, this is the basic concept of it. All right. For the next one, when we have 3 blocks, okay, in this case we have 3 blocks, okay. Just now we have 2 blocks, okay, 2 blocks. This time we have 3 blocks, okay, which is the case for 2 degree of freedom. Okay, just now we have 1 degree of freedom, 1 degree of freedom. Okay, this time we have 2 degree of freedom. Okay, for 2 degree of freedom, we have here, we have 3 blocks, right? Block A, block B, and block C. So we have here XA, okay, for block B, XB, and then we have block C, right? So we have 2 pulley here, 2 and 2, this is 1. So you have 2XA plus 2XB and XC equal to constant, right? So as I mentioned just now, the first step is very important, okay? The way we set up the equation for dependent motion, the first step is very important. And then after that, the rest will follow. When you do the differentiation, we differentiate with respect to time. For example, for this the position of these 3 blocks, okay, you differentiate with respect to time, you get the velocity. You get 2VA, 2VB, and VC equal to 0. And then for the acceleration, again, you differentiate with respect to time, you get 2 acceleration A, 2 acceleration B, and acceleration of C. Okay. All right. This is an example. All right. So I expect you to go through on your own 11.5. For the graphical solution. Graphical solution. All right. For graphical solution, I just want to highlight this slide. What does it mean by this graphic for rectilinear motion? Okay. So what we have here is the first one, which is this one, is the graph of x versus t. Okay, graph of x versus t. So you have x and t, and then you get the slope of it, the tangent. Okay, the tangent of at this curve. Okay, so basically, what is this tangent? Okay, what does it mean by this tangent? Basically, it's the slope. Okay, the slope. I take 1. This is at this instant. So meaning the slope of this graph is basically the velocity of it. We do differentiation dx dt. Okay, so you get v. Okay, so the slope. Okay, the slope of this graph is the velocity. Right, is a velocity. And then we move to the next graph, which is the graph of v versus time, right? So you plot the graph, okay, V versus time, okay, you get this curve, right? You get this curve. You get this curve, okay, this curve. And then you get the slope of it. So the slope of it is an acceleration, okay? After you have obtained the this graph, and then you can plot the acceleration plot, which is this one, right? All right. This one shows you the area under the curve, okay? This is area under the curve, acceleration versus time curve, okay? This is area under the curve, right? Acceleration, and then the velocity, area under the curve. So the integration basically is area under the curve, okay? This is for acceleration, this is for the velocity, right? And then this going back reversely for to find the value of x, okay? So for mass moment of inertia, this one we're going to cover in during the topic of rigid body. Okay, we're going to do the revision again for mass moment of inertia. So I'm not going to go into detail of this for today. All right. Okay, we stop here for 5 minutes. Okay, we take 5 minute break. And then after this, I'm going to cover the topic of curvilinear motion. Okay, position, velocity, and acceleration. Please sign up your attendance in our Google Classroom for today. Okay, just write down your name and then your ID, student ID in the wall of our Google Classroom. Okay, thank you. So we'll come back at 9:07. Okay, welcome back. Make sure you sign up your name in our Google Classroom. So for first group 14 and another group 7. So we need more. Need more to sign up there. All right. The next topic, the section that I'm going to highlight here. If in earlier slide we have covered about rectilinear motion, now we talk about curvilinear motion. Okay, so for curvilinear motion is when the particle move along a curve. Okay, so if the particle move along the curve other than a straight line, so it is called a curvilinear motion. Okay, curvilinear motion. If you look at this figure, okay, this figure on your right hand side, left hand side. So we have here the particle. Okay, this particle move along this curve. Move along this curve from P to P prime. Okay, P to P prime. Okay, and we have the curve here. Okay, the length of this curve is delta S. Okay, delta S. Okay, so we analyze what happened here. Okay, along this curve from P to P prime. Okay, the distance from P to P prime we have delta S. Okay, delta S. This curve, right? Okay, that is the first one. The first thing that I highlight. Secondly, we have here the X, Y, and Z axis. Okay, we have the origin. Okay, so from origin to P, okay, so we can have what we call a position vector. Position vector, okay, position vector, okay, which is this one, position vector. Okay, this is a position vector. Okay, this is position vector from O to P. Okay, O to P. Okay, and then I want to highlight also, how about P prime? Okay, so we have another position vector. I name it as R prime vector. Okay, this is R vector. This is R prime vector, referring to P prime. Okay, so what happened? What will be the position vector from P prime to P? So we have another one which is what called delta R. Delta, right? So from this figure, okay, the first one, this is the first one. First one. Second figure, we have remember small changes of delta R, delta T, okay, which is dr dt, right? Dr dt. And then same thing here, we have instantaneous, we call it instantaneous velocity. Okay, so we have here the velocity, okay, equal to dr dt. This is instantaneous velocity. And then here we have we can write as ds dt. Okay, okay. I hope you can differentiate between R and S here. Okay, R and S is not the same, right? Because R we talk about position vector, and S is referring to the length of the curve. Okay, which is here from here to here. So you move along this curve, right? So we have here instantaneous speed is ds dt, and then we have here instantaneous velocity, which is vector. One vector, one scalar, right? one vector, one scalar. Okay, this is the another figure. The third one we have, this is S, and then this is V. Right? Instantaneous speed, instantaneous velocity. Next one about curvilinear motion. We have mentioned position, velocity. Now talk about acceleration. Okay, for acceleration, we refer to this figure. Sorry for the interruption. Uh, we have we can find the acceleration. Okay, so we have the acceleration is going to be, okay, acceleration here is dv dt. All right, dv dt. This is what we call instantaneous acceleration. Now you can see the difference between instantaneous acceleration, okay, which is a vector, right? Which is a vector. So in general, what we can say about acceleration, okay, acceleration vector, um, acceleration vector is not tangent to the path and the velocity vector. Okay, all right. Okay, for this one, the derivation of vector function, I have explained yesterday. I think I don't want to repeat this one because we have do the revision of vector function yesterday. Okay, how to do the derivation of vector sum and derivation of product and dot product. So I'm not going to cover it again, but you can, for the sake of to strengthen your mathematics, I think you can go through this derivation for product of scalar and dot product and cross product on your own. Okay, next one is a rectangular component of the velocity and acceleration. Okay, okay, you look at this figure. Okay, look at this figure, what we have here. So what we have here, basically we have I put, you know, to make it clear, this is 3D. We put this in the box like this. Okay, we have particles p. This particle p, okay, this particle p move, okay, along this path, okay, this particle, and then we can obtain the position vector of this one. We locate this one, this particle, position vector of particle p by its rectangular components. So we have here position vector r. So we have xi, y, j, and zk. Okay, okay, this is the position vector of it. Okay, in terms of I, j, and k. Okay, we have a unit vector here, I, j, and k. And then second step is we want to find the velocity vector. Okay, so for the velocity vector, what you need to do is we start by writing this one. Okay, all right, start by writing this one. okay, we start having this one, right? The position vector. Okay, this is position vector. And then second one, we will find the velocity. Okay, so we differentiate this one, right? So you get r dot here. Okay, so for r dot here basically is the derivation of the rdt. Okay, so v equal to dr dt. So this is dx dt, then this is dy dt, and this is dz dt. Okay, so this one dx dy dt, and then dz dt. So basically, what is dx dt? Dx dt, okay, is x dot. Okay, dy dt is y dot. Okay, and dz dt is z dot. So we have it here. Okay, this one, and this one. Okay, so we can represent the velocity vector also in the form of here. Okay, in the form of vx, in the form of vy, and in the form of vz. So different type or ways to represent. Okay, so for the sake of consistency, you can use, either one of these. If you want to use x dot, y dot, and z dot, yes. Then consistently for the next one, to find the acceleration, we differentiate one more time. Okay, one more time, we can differentiate one more time to find the acceleration of it. Okay, so what happened for the acceleration? Basically, we do another integration, so it will become x double dot, y double dot, and z double dot, and we can write as the following. Okay, so these are the step on of how we can write the rectangular component of velocity and acceleration. Okay, for vector of particle, and velocity vector, and acceleration vector. All right, another one. This one, I think this concept is not new to you. Okay, you've been exposed to this type of problem uh, during your high school, as early as in high school, which are the projectile motion. Okay, so I just would like to highlight the fundamental of it. We have here the rectangular component. Okay, we have component acceleration, where we can integrate independently. So this is the case of motion of projectile. Okay, projectile. We have a cannon here. I name this one as point of origin 0, and then we project, with the initial velocity of v dot. Okay, so this initial velocity we can resolve it into x and y direction. Okay, so this is vx, and this is vy, y dot. Okay, and then we project, this cannon, for example, going up. Okay, and until it reach the maximum height or certain height here, which is y. Okay, and then it goes sometime, and then we will have the gravity. Okay, gravity attract to bring it down, and then after some time it will drop to the ground, and then we measure the distance, how far it will go. Okay, how far it will go. Maybe later on become the blasting engineer or cannon engineer. So they have to do this type of simulation, what will be the range, how far it will go. Okay, what happened to the blastings, and then that one also under mechanical engineering, and you have to do dynamic study, impact study. So we have here, we have the initial condition, and then we have to integrate to the integration. Okay, And then the thing that we need to know, the motion in horizontal is uniform, and motion in vertical direction is uniformly accelerated. Okay, uniformly. Remember the keyword of uniformly accelerated, meaning we can use the formula of a constant acceleration that we have explained in earlier slide. Okay, all right. So the main concept is from here, right? I'll give you 1 minute to read this slide. This one is related to relative motion to the frame in translation. Okay, for motion relative to frame translation, okay, again, we have this frame. Designate one frame as a fixed frame of reference, okay. So we have two axes here, okay. The first one, the black in color, O, X, Y, and Z, okay. And then we have another axis, which is X prime, Y prime, and Z prime, okay. So we refer to a fixed frame of reference, which is O, and then we have another frame here, okay. We have point A, but okay, and point B, okay. Remember, we must have the same reference, which is at origin. So we have position vector R here. This is position vector RA, and then for particle B here, we have position vector of RB, okay. And then we have here RB relative to A, okay, RB relative to A. So what I'm trying to say here is when we want to find the vector position vector B relative to A, okay, joining A and B define the position of B with respect to moving frame A, X prime, Y prime, and Z prime, okay. And then we want to find the velocity and acceleration, we differentiate it, okay, twice, okay, twice in order for us to get the acceleration. This is the concept of relative motion relative to frame in translation. The next concept is the concept of tangential and normal component. Okay, this concept also I think is not new to you. We have here if you refer to this particle moving along the curve, okay. So when I want to draw the line, what we call here, this is if before unit vector, remember unit vector I, J, and K, but for the case of tangential and normal component, we have unit tangent and unit normal. Okay, so I denote as unit tangent and unit normal as the following. So unit tangent, I name it as ET. Okay, ET, which is perpendicular to the path here. Okay, we have the path here. Particle move along this path. So it is tangent to the path, so this is unit tangent. And then this one is perpendicular to this unit tangent, we have unit normal, okay, which is denoted as ET, okay, ET, all right. So we can have the following equation. The way I denote it as, we can write it by using this formula, okay. What I would like to highlight here is we want to express acceleration vector, okay. So our intent is to express acceleration vector in terms of tangential component and normal component, okay. This is our intention here, okay, what we intend to do. So we have here ET, okay, ET, okay. Some book they say they put like this, but we did not like this, okay. ET, and this is we call a tangential unit vector, okay, for particle path P, okay, particle path P. For this one, I'm referring to this one. We talk about P first, okay, and then we have uh, unit normal here, which is perpendicular to this ET. So unit normal, okay, N. All right. So how do we define unit normal and unit tangent? So basically, unit normal is the derivation of unit tangent with respect to theta. Because we talk about angle, right? Angle. This angle is referring to here. We have E, ET, and then ET prime. This is ET, this is ET prime. So we have from O prime, it is rotated with angle of delta theta. So this delta theta basically is delta ET. Okay, so we differentiate it, and then you get you differentiate with respect to time, you get E dot T, which is theta dot E theta. Okay, all right, and then with the velocity vector express, okay, we express the velocity to be v equal to et, okay, okay, v equal to vt. All right, then we substitute. After you substitute, we get the following for the acceleration. Okay, so I want you to write in your formula sheet, okay, for tangential and normal component, we have this equation. This is important equation, and also you have here, okay, tangential acceleration, we have dv dt, and then you have, okay, and then you have normal acceleration, we have v squared over rho, and then unit normal, okay. Okay, graphically this is how it looks like, okay. It's going this way, and then you have the value of this one, okay. All right, this is important for you to highlight, write down in your formula sheet to refer later, okay. Okay, for circular motion, this is a tangential and normal component. What I'm trying to say here is we have this figure, we have the plane, okay. On top view, you can see we have ET and then EN, and then what we have here basically EB. What is EB? Okay, EB basically, okay, basically this one lie on this plane. It's lay on this plane. So we have ET, okay, cross EN, okay. So this is principal normal, and EB is binormal. Binormal mean, you know, it divide this into two, okay, perpendicular to it. Okay, this EB is pointing out, going out. Okay, so plane containing tangent and normal unit. So this vector is called osculating plane. Okay, osculating plane. Okay, another concept that we need to use here for this topic is radial and transverse component. Okay, for radial and transverse component, we have the particle moving along this line. Okay, and then you have this particle start from origin. You have certain angle, which is angle theta. Okay, this angle theta. So you have unit radial, which is along this line, along this line. So you have unit radial, and then perpendicular to this unit radial, we have this is what we call unit transverse. Okay, we have unit radial. This is radial, and then this one is transverse. Okay, unit radial and transverse. So we have this equation, which is R equal to R unit radial. Okay, okay, and then we have we differentiate the R. Okay, dr der. Okay, respect to theta, you get E theta. Okay, and then you differentiate der respect to time, you use the chain rule. Okay, der d theta dt. This is what we call chain rule. Chain rule. Same thing here, de theta dt equal to de theta d theta dt. This is chain rule. Chain rule, use chain rule. Okay, so you get E theta d theta dt, and then minus er d theta dt. Okay, for the case of 3D, we involve what we call this cylindrical coordinate. Okay, cylindrical coordinate. Okay, we can express the velocity and acceleration, okay, using unit vector er. Okay, er, e theta, and k. Okay, because 3D, 3D it involves z direction. So you have we can denote it as er. This is r, er. This is how we have the unit vector of it for cylindrical coordinate. Okay, so we have here er. This is er, and then this is e theta, and then k. Okay, so these three unit vector. So from there we can find the position vector, the velocity vector, and acceleration vector. Okay, this is position vector of the particle, and then this is theta. Since it's cylindrical, we know what will be the theta, and then this is r, okay, and then the height of it. Okay, okay, starting from here, the basic concept, we have theta, we have r, and then this is the location where the particle P is located, which is the height of it is at z. Okay. All right, we do this example. Example 1110. Remember, now we are using non-SI system, British unit, US customary, in miles and in feet. Okay. So motorist is traveling on the curved section of the highway. Okay, 60 miles per hour. Okay. And the motorist applies brake, causing a constant deceleration. Okay. Knowing that after 8 seconds the speed has been reduced to 45 miles per hour. Find the acceleration of the automobile immediately after the brakes are applied. Okay. So what is known here, we know the velocity. Okay, the velocity of it. So, and then we know the radius of curvature here, which is the radial of it is 2500 feet. Okay, so you have to find what will be the acceleration of the automobile after the brakes are applied. Okay, so we need to calculate tangential and normal component of acceleration. Okay, and then we need to find acceleration magnitude and direction with respect to tangent to the curve. Okay, tangent to the curve. Okay, so these are the two things that we can, you know, our plan to solve this problem. Calculate tangential and normal component of the acceleration, and then you find the magnitude of the acceleration, okay, with respect to tangent to of the curve. Okay, so we start with this one. First thing is the unit. Conversion unit is very important. Okay, so because we want to make it consistent, because you are given here miles per hour, mile we have to convert to feet. Okay, batu convert to feet. Okay, all right, miles per hour. So mile per hour you convert to feet per second, right? So 60 mile per hour equal to 88 feet per second. That use a conversion. Okay, 45 mile per hour equal to 66 feet per second. Right? So 2.5. All right. Reduce to 45. Okay, 60, 45. So you calculate tangential and normal component of acceleration. Okay, this is the first thing. Calculate the tangential of it and normal, and then you find the magnitude and the direction. Okay, this is the answer for this sample problem. Okay, so another sample problem is 11.12. Okay, which is the application of the concept that we learned just now. Okay, we have a rotation of the arm O defined by theta. Okay, 0.15. Theta is in radius. Collar slide along the arm. Okay, as the arm is rotated, the collar also will slide along the arm with the equation of R equal to 0.9 minus 0.12 t square. Okay, t is in meter. So what you need to find here is the arm rotated 30 degrees, and then what will be the velocity of the collar? It's number one. What will be the total acceleration of the collar? Okay, number two. Number three, what will be the relative acceleration of the collar with respect to the arm? Okay, So these are the three important aspects that you need to know. Okay, you need to do. So first thing you need to do is evaluate T. Okay, evaluate T at theta equal 30 seconds, because we have taken 30 degrees. The question asks us what happened at 30 degrees, so we evaluate what the time, okay, for theta equal to 30 degrees. Okay, that is the first thing you need to do. Secondly, you need to evaluate radial and angular position. Okay, okay, evaluate radial position, angular position. So we have here theta, and then you have r, you have theta. This is important information that being given in this problem. You have r, we have theta. So you evaluate this one, and then you differentiate one, you differentiate twice. You get velocity, you get acceleration, right? Next one, you calculate the velocity and acceleration by using cylindrical coordinate system. So you have the formula at hand at your formula sheet already. So you just substitute using that formula of the cylindrical coordinate system. You can calculate the velocity and you can calculate the acceleration, okay, by using cylindrical coordinate. Okay, and then you evaluate acceleration with respect to the arm. This is we talk about relative motion, relative velocity, and relative acceleration. Remember, so this time velocity of B, which is the color with respect to the velocity of the slider. So the concept of relative motion is important. Yeah, right. Okay, this is the solution, how to do step by step. Okay, you can do this one also on your own. Evaluate T for theta equal to 30 degrees. We evaluate radial and angular position. Okay, and then these are the formula that I have mentioned just now for you to do the calculation of the velocity and acceleration. This is the formula that you need to have in your formula sheet. Okay, velocity equal to VR ER plus B theta E theta, and then acceleration AR E theta, A theta E theta, right? And then this is the answer, and it shows here the direction of it graphically. And then this is the evolution, how to find acceleration with respect to the arm. Okay, A, B, this I mentioned. Acceleration of B with respect to this arm, OA. Okay. If you would like to get the detailed solution of this one, you have to refer to the textbook. Okay, go to a library or you can download in internet the PDF book of Beers and Johnson and go through this example carefully step by step. Okay. All right. I think that's all for today. Tomorrow, since tomorrow I have a meeting in USM Kelantan, so we are going to have our makeup class tonight at 8 p.m. until 9 p.m. Okay, so we have our class tonight as a replacement for tomorrow. So class, makeup class tonight at 8 p.m. until 9 p.m. Okay, so I'll see you tonight. Before we finish the class for today, you have any question? Don't forget to sign up your name. Okay. Okay, group B, 20 students already signed up. And for group A, only 14. I think 10 more students didn't sign up yet. Okay, do you have any question? So this Friday, we are having our first quiz, so please get ready. The topic of chapter 11, chapter 11. which is kinematic of particles. Okay, if you don't have anything, so I'll see you tonight at 8 p.m. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh.
Walaikum assalam. Thank you, Doctor.